Hey, so guys, before we get started, there's a couple things that we need to talk about, but we are actually getting started. First of all, this. Guys, amazing turnout at remediation. We actually went back and collected the data, and of all of the people that could take advantage of remediation, 90% of you did. And that's terrific. Guys, it's an amazing way to start the year. I'm going to follow up with the people that chose not to eventually and find out why they didn't. But guys, that's amazing because it tells us that you're interested in learning the material, that you're invested in what you're doing. And guys, that's a good thing. So that's super cool. And congratulations for those of you that are engaged and great news. Well done. So guys, with that said, I need to tee up the ball for you today before we get started, because there's the possibility that today could create a little bit of tension. And so I want to talk with you about this just so that you feel free to enjoy what we're going to do without that tension. So guys, today, the first thing that we're going to talk about is where do atoms come from? And guys, as we talk about the answer to that question, we are going to talk about something called stellar evolution. And guys, this is where we've got to pause. I'm going to plop down and we're going to have a little family meeting. So guys, here's the deal. We actually get to use the word homogeneous. What does homogeneous mean? The same the whole way through, right? So guys, here's the deal. You may not know this, but living in Utah County, you live in one of the most religiously homogeneous places in America. You understand that, right? And you also understand that I am not a part of that homogeneity. I am not LDS. But guys, the reason that I bring this up is because the thing that we all do share, well, many of us share, is a faith that is very meaningful to us. If you don't, that's fine. And you're making those choices on your own, and that's awesome. But guys, understand, just because of averages, we all, well, not all of us, but many of us in this room have a faith that defines in many ways who we are. And guys, this could be the tension, because today we're going to talk about evolution. And guys, the minute we start talking about evolution, it becomes God and it becomes science and it becomes monkeys turning into people and all these other misconceptions about what evolution means. And guys, evolution simply means change. And so as we talk today about this idea of stellar evolution, we're going to talk about the science. But guys, I would propose to you that you don't have to make a choice. And for many of you, as you get further and further along in your studies, you get to university, you start thinking about even majoring in a scientific discipline. Guys, even at BYU, your faith is going to be challenged. And people are going to say to you, you can either be a person of faith or you can be a person of science, but you can't be both. And guys, I strongly reject that notion. You can fully be a person of faith and also be a person of science, and you don't have to choose. Now, guys, understand, I can't talk with you about how I make sense of that. That's not part of the curriculum. If you want to talk individually, and if you come and ask, I'd love to share stuff with you, but I can't say that from here because it's not a part of the curriculum. But guys, I can say this. What we're going to learn today in no way invalidates or challenges any faith that you might have, because science and faith are actually complementary and not in tension. So, with that said, guys, what are we going to do today? And the answer is this. We're going to actually answer 3 questions today. We're going to talk, first of all, about where do atoms come from? Stellar evolution. Then, guys, after that, we're going to talk about what are atoms like. And, guys, this is mind-boggling stuff. I love you'll see. It's nerdy. It's awesome. It's really crazy stuff. And then, guys, finally, the last thing that we're going to do is we're going to talk about what are atoms made of. You already know protons, neutrons, and electrons. We're going to dig a little bit deeper. That's going to be the end of our day, and you're going to get your homework done. You guys ready to go? Let's do it. All right. So guys, this then is the deal. All that you need to write down is the stuff that's on this paper. If it's not on this paper or a fill in the blank on this paper, guys, do not write it down. But with that said, let's get started. So guys, why are we talking about atoms in the first place? And obviously the answer is because it's the bedrock of everything we've been doing, because elements make up everything in the universe. So guys, what we're going to do first is we're going to talk about this. Pre-read these questions with me. Guys, in the next 4 minutes, you're going to be able to answer these 5 questions. Question 1 is this: where did all the hydrogen in the universe come from? Guys, if you're not familiar, hydrogen is element number 1. It's got 1 proton and 1 electron. It's the simplest element in the universe, and we're going to talk about where it came from. You may be wondering, why do we care? You'll see. Then guys, question number 2 is this: what are stars? But guys, in order for this to be meaningful, we need to talk about one thing that maybe you don't know. Guys, what is the closest star to Earth? The sun. You guys understand that? That the sun is a star, and if there's intelligent life in other part of the Milky Way, they are looking back at our sun, and it looks like any star that's in our heavens. It twinkles, it looks just like a star. Guys, our sun is a very, very average star. Then guys, number 3, what are the heaviest elements that stars can produce? Then guys, number 4, where do elements heavier than iron come from? Which frankly kind of answers question number 3. And then guys, number 5, what's the heaviest element in the universe? Zach, go ahead. Oh, do you already know? Yeah, and so we're going to get into it in just a second. So guys, you understand where we're going? So how are we going to get there? And guys, the answer is we are going to put ourselves in the trusted hand of a guy named Neil deGrasse Tyson. You guys know Neil? Yeah, sadly, Neil is becoming more and more uppity and political as he gets older. He actually did a devotional at BYU a couple years ago, a Tuesday devotional, and he actually wouldn't let BYU record it. But anyway, it doesn't matter. So guys, let me explain to you what you're looking at on the screen. Follow me over here and let's talk. So guys, today what we're going to do is we're going to build a timeline. And this wall, well, this counter right here is 13.8 billion years ago. And guys, over here at the windows, that's going to be today. So here we go. So guys, why did we make this counter 13.8 billion years ago? Do any of you know? Was that you, David? Talk more. So it's about the Big Bang. What do you know about it? Say it again. It's a big explosion. Do you know what exploded? Don't know. Guys, what else do you know about the Big Bang? Go ahead, Zach. Yes. Yeah. Good for you. That's awesome. What were you going to say, Cole? It did. Well, yeah. And isn't it interesting how we say created everything, but you can sort that out later. So guys, it goes like this. 13.8 billion years ago, the entire universe. Guys, not just Orem High, not just Earth and the moon, not just the solar system, not just the Milky Way. The entire stinking universe was in a ball the size of a golf ball. You can't even wrap your head around it. But guys, this is what happened. And 13.8 billion years ago, and Zach, you mentioned the little thing. Do you know the name of it? It's actually called the singularity, the oneness. And so guys, this thing called the singularity 13.8 billion years ago exploded. As David said, there was an explosion, and it was a stinking big explosion. We call it the Big Bang. And guys, as that happened, the universe expanded. And as it expanded, it cooled down. And as it cooled down, eventually it got cold enough that protons and neutrons and electrons could start to stick together. And as they did, they made the lightest element in the universe called hydrogen. And so guys, that's this. This is an artistic representation of our universe a couple million years after the Big Bang, when it was literally just a big, cloud of hydrogen gas. And that's where the video picks up. Go ahead. Amazingly, no, it didn't. But you're absolutely right. That is where black holes come from, is other things collapsing on themselves. But the physics of this is such that actually it couldn't collapse anymore. And so consequently, it didn't collapse. But this is the problem. We can't answer two important questions. How did it get there and why did it explode? Right? Because 13.8 billion years ago is as far back as we can look. Because before that, there was no time. And if there was no time, whatever it was that was before that, that put that thing there, that made it explode, science can't answer that question. So we don't know what happened before the Big Bang. And it's impossible to know. You can't look deep enough into space to figure that out. It's crazy stuff. So guys, if I set the stage okay, you understand what you're looking at? This is the universe just a couple million years after the Big Bang. Big ball of hydrogen. Here we go.
As hydrogen piles on,
Turn the
the
volume
central region grows more and more dense until something.
Okay, starting over. So guys, here we are looking into this ball of hydrogen.
As hydrogen piles on, the central region grows more and more dense until something brand new lights up the universe. A star.
So guys, what's going on here is hydrogen, like anything with mass, has gravity. And these hydrogen atoms are all attracted to each other and they start to cluster together into balls. That's where stars come from.
These first stars are hydrogen giants.
By the way, guys, don't try to answer these questions. We'll go over, just watch the video. We'll come back and answer the questions in a minute. Sorry, I should.
100 times or more larger than our own sun. Such massive stars are short-lived, 2 or 3 million years at the most, and they go out with a bang. An explosion so big, they've been dubbed hypernovae. And it's with these cataclysms that the universe begins to accumulate building blocks of life. All the atoms in the universe heavier than hydrogen and helium, forged by stars.
Stars are really interesting. They don't just sit there, because they last so much longer than we do. Stars are the oldest stars. They turn light elements into heavy ones. They get the energy. Star begins as light made out of hydrogen and helium. There's about 70% hydrogen, 28%.
And guys, that's true for our sun as well. Our sun is just a big ball of hydrogen that's turning hydrogen into helium.
Case of the sun.
In a star's core, the temperature and pressure are so high that hydrogen atoms fuse together to make helium. Hydrogen fusion releases prodigious amounts of energy, heat and light of a star.
That's the story for 90% of the life of a star, using hydrogen to make helium.
Eventually, the star runs out of hydrogen and begins to fuse its stocks in helium, making it yet heavier elements.
And so the way it works, and it always works this way, is that it contracts and it gets hotter. And if you can find something to burn, whether it's the kitchen sink, coal, or whatever, it's burning helium.
Taking 3 of them to make carbon.
You can add one more helium to that carbon and make element number 8, oxygen.
That's a tremendous step forward. You get carbon and nitrogen and oxygen made in stars.
Now this is great because on the board we already have principal elements of life.
Organic chemistry is the chemistry of carbon.
Carbon fuses next, it's still heavier elements.
Sulfur, argon, chlorine,
Stand different tastes.
fast. Back in the middle, silicon starts to burn 1.5 billion degrees. Stupendous temperature.
Mixed with helium, vanadium, chlorine,
Cobalt, nickel, iron.
By the way, guys, in the next unit, you're going to find out why. It's fascinating.
And so, when a star builds up too much iron, it dies.
The core collapses, it bounces,
It begins to move out, first slowly and faster and faster.
and that sends a very sharp wave back out through the star.
And now what was falling down is going out, the whole thing blowing up. A supernova.
The supernova explosion can be as bright as 4 billion stars like the sun.
A stupendous explosion.
Such outrageous energy is overcoming the iron barrier, cooking atoms into all the rest of the elements in the periodic table.
So starting down here, you can go copper, gallium,
germanium,
arsenic,
zirconium, niobium, lithium,
strontium,
rhodium,
terbium,
thorium, iodine, calcium, barium, thorium, none. That's enough elements.
We are all starters. Carbon in our bodies, iron in our blood, calcium in our bones. Every last atom is formed in a star.
Crazy stuff. So guys, let's answer the question, shall we? We now have enough information to go through and answer these, but let's start at time 0. 13.8 billion years ago, Big Bang, singularity, boom, here we go. It expands and it cools, and as it does, it starts to form hydrogen. So guys, where did all the hydrogen in the universe come from? The Big Bang. And guys, that continues to be the case. All of the hydrogen that we see in our universe can trace its origins back, well, to the Big Bang and also radioactive processes. We'll talk in the next unit. So, question number 2. What are stars? What are they made of? Hydrogen turning into helium and other heavier elements. So, guys, these are just big balls of hydrogen. And they're fusing together the hydrogen to make helium and other elements. And guys, understand this is it's not a chemical reaction. These atoms are actually locking together nuclei to nuclei, and they're releasing a pant load of energy that we experience as sunlight. The heat of the sun. You guys hearing that hum? Here, let me see if I can fix it. Oh, there we go. All right. We've got a little bit of a feedback loop in my amplifier. All right, so then guys, moving along, what is the heaviest element that a star can make? Iron. Yeah, guys, iron's the end of the road. Just a little teaser for the next unit. The reason, guys, is you know how you learned in biology that the electrons and atoms are organized into rings? So are the protons. You've already just drawn them as a mucky muck of stuff and a little plus sign. Guys, the electrons are organized into rings as well in the nucleus of an atom. And in iron, all the rings are full. We'll talk more later. Then, guys, what about this? Where do the elements heavier than iron come from? Did you catch it? Supernovae. I don't even know. Novae, nova, I don't know. Those things. So guys, when these things explode, energies, what'd they say, like some millions of times the brightness of our sun? Like crazy stuff. How many was it? Yeah, it's ridiculous, guys. And it's that energy that can even force things like iron to fuse together and make heavier and heavier and heavier things until we get to the heaviest element that can be supported in our universe, which is uranium, and that's the end of the road. But guys, of course, I think we've already talked about this. There are elements heavier than uranium, right? But where do they come from? They're all man-made. Yeah, they don't exist but for us. We make them. Oh my gosh. So yes and no. So some of them, and you'll notice if you let your eye scan across the periodic table, a lot of these heavier elements have very little data because they're such small samples we can't measure them. That said, we made enough plutonium to destroy Nagasaki. Right? So some of these super heavy elements, we have literally tons of it. Some of it we have 3 and 4 and 5 atoms, and that's all we'll ever get. We're going to actually watch a video in the next unit where they talk about the creation of element 114. And actually they create this in groups of like 10 and 20 atoms. Yeah, it's unbelievable. They actually take sodium and smash it into 94, which would be what? 94 is plutonium. So they take plutonium and sodium and smash them together to make one. Yeah, it's fascinating. So guys, are you good on all the answers? You feeling? Oh, Zach, please.
Is that a hypernova? Is that like a bigger?
Yeah, so that's neat that you caught that. So he talked about the idea that these original stars, way billions of years ago, they're called gas giants. They're huge on a scale we can't even imagine. When those blew up, and actually still do blow up, there's still some of them on the edge of the universe. Those go what they call hypernovae. Normal stars like our star, like our sun, is eventually going to go supernova. It's going to blow up, burn up the entire solar system. It's going to be a tough day. But it's going to be millions of years, billions of years from now. But our sun will go supernova. These are bigger stars and they go hypernova. So, yeah. So it's going to be a tough day. But it's not going to be in our lifetime. So, guys, questions about any of this? You guys good? All right, I'm glad you guys are enjoying this. Now we're going to do question number 2, which you can't see because my writing tools are in the way, but you can see it on here. Guys, the question that we're going to talk about now, and we're now on that next page, is how small are atoms? They're pretty small, but guys, the question is how small? And I know this is a sobering thought, but guys, imagine being my child. Imagine how nerdy that would get. So, guys, you know from my little introductory pictures that I showed you a month ago that every summer we go to the Oregon coast, right? And I get a little nostalgic sitting up on the bluffs, looking out into the ocean, feeling small and yet wonderful. But guys, have you ever been to the ocean? Have you ever looked out over the ocean? Can I change your life? Guys, wrap your head around this. Luis, don't miss this. Wrap your head around this. Guys, if you could go out into the ocean, and if you could scoop up a cup of water out of the ocean, there's water molecules in there, right? These guys. There's water molecules inside that cup. You ready for this? There are more water molecules in that cup of seawater than there are cups of seawater in all the oceans of the planet. Yeah, let's say that again. So guys, when you're holding a cup of seawater, there are more water molecules in that cup of seawater than there are cups of water in all the oceans on the planet. So imagine if you went into the ocean and tried to drain it with a cup. 1, 2, 3, 4, and you drain the Pacific and then the Atlantic and then the Indian and then and all the oceans. Guys, there would be more water molecules in a cup of water than there are cups of water in all the oceans on the earth. Because that's how small water molecules are. Isn't that crazy? Guys, that's how small water molecules are. So now you understand that we're talking about something that's almost impossible to visualize. But guys, the next time you go to the ocean, take a second and just sit there and wonder that all of those oceans are made out of molecules that are so stinking small that that relationship is true. It boggles my... It's bordering on spiritual. You can sort that out. So, guys, with that said, how on earth do we talk about something that stinking small? Well, guys, what you're going to see is what we have to do is we have to rely on analogies. And what we're going to do is we're going to watch a TED Talk where a university professor actually shares some of these analogies. Now, guys, I got to warn you, some of this is a little disturbing. It's actually a university professor cartoon in this weird jumpsuit with bloodshot eyes and gorillas. You'll see. It gets weird. But don't let the weird get in the way of the amazing. Guys, this video I'm going to stop along the way as we play with this. Did any of you watch TED Talks? Yeah, fast guys. If you're nerdy like me, go to TED.com. Unbelievable stuff. It's I'll tell you the story about Ted later, but it's really cool.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer
Why the mouse?
I don't understand.
No idea. Stick with it.
is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit?
Okay, so stop. Picture a grapefruit. It's like a big orange, right? How many atoms are in a grapefruit?
Well, let's assume that the grapefruit is made up of only nitrogen atoms.
Hey guys, the reason they're doing that is because to do the math, we need to know the size of the atom, so he used the size of nitrogen. Keep watching.
Which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry.
Okay, so now you got to pause. So here's what we're doing. We're taking a grapefruit and we're taking the atoms in the grapefruit and we're expanding those atoms to the size of blueberries. Now guys, when the atoms get bigger, the grapefruit gets bigger, right? How big does the grapefruit get if the atoms become the size of blueberries?
And then how big would the grapefruit have to be? It would have to be the same size of, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit?
All right, stop. Guys, this is stinking ridiculous. Guys, when you go out to lunch today, look at the Earth. And then look down and imagine that the entire Earth that you're standing on is full of blueberries. That's how many atoms are in a grapefruit.
That's right. So how big's the atom? That's really, 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 really small.
You find that disturbing?
Yes.
Yeah, me too.
And you know what? It gets even more crazy.
Okay, so now guys, what we're going to do is we're going to go inside the atom and we're going to talk about the nucleus of the atom, the middle, where the protons and neutrons are. How big's that?
Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a two-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball
Lavelle Edwards Stadium.
the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble.
All right, so guys, this is our visual of an atom. Imagine that you're kneeling at the 50-yard line of Lavelle Edwards Stadium, and in your hand you have a marble. Guys, that is the scale of an atom. If the nucleus of an atom is the size of a marble, the football stadium is the size of the whole atom. But guys, what else is in the atom except for the nucleus? Electrons. And where are the electrons? They are running around the cheap seats in Lavelle Edwards Stadium. So guys, what else is inside of an atom except for the marble and the electrons in the cheap seats? What else is inside an atom? Do any of you know? Nothing. Guys, the atoms that make up everything around us are 99.99999% empty space. And yet we're solid. Guys, there's as much empty space in every single atom as there would be empty space in Lavelle Edwards Stadium with a marble in the middle. This is freaky stuff. Let's come back.
And there's more. If I haven't blown your mind by now, let's Let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium with a nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons?
And what's the answer? Nothing. Guys, it's stinking empty. So now the question becomes, why are we solid if it turns out that atoms are mostly empty space? And guys, the answer is solid is an illusion. We're going to talk in the next unit.
Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing.
Why the gorilla? I have no idea. I like it, but it's...
Can even get more bizarre.
All right, so now, guys, we're going to talk about this. We're now going to talk about the nucleus of an atom, and you understand it's stupid small, right? Marble inside of a football stadium. But guys, what's inside the nucleus? Well, protons and neutrons. And guys, protons and neutrons are heavy. So we've got mass in a very small volume, which means the density is crazy high. So now the last thing we're going to talk about is how dense is the nucleus of an atom.
Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed.
Got it? A lot of numbers. Kind of meaningless.
But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet.
Got it?
No.
Me neither.
Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot.
And so I did. It's actually right here. So guys, this is a box that is 1 foot by 1 foot by 1 foot. Right now, this isn't very dense because the only thing inside of it is air. The question is this: how much matter would we need to put inside this box in order to make the matter inside this box as dense as the matter inside the nucleus of an atom? You ready?
And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus?
So guys, imagine this. Imagine trying to shove a car into here. What are the chances? 0. But it gets worse.
Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth.
So guys, in order to make the matter inside this box as dense as the nucleus of an atom, we have to jam 6.2 billion cars inside that box. And then that would be as dense as the nucleus of an atom. You starting to get the sense that these things that make us up are stupid crazy? They're small on a scale that we can't even imagine. They're mostly empty space, and the nucleus is crazy dense. It's pretty cool stuff.
So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of the nucleus.
So guys, let's review.
So I'm saying that if you took every car in the world and put it in your 1 foot box, it would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small.
So what do we think of when we think about how small the atom is? Blueberries in the earth. You're going to be writing about this in your homework assignment today. When we think about the size of atoms, we're thinking blueberries inside the earth.
Think atoms in a grapefruit, like blueberries in the earth. The nucleus is crazy small.
So when we think about how small the nucleus is, what do we think of? Marble inside a football stadium.
Now look inside the blueberry and blow it up to the size of a football stadium, and now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space.
Again, the football stadium.
The nucleus has a crazy high density.
Guys, what do we think about when we think about the density of the nucleus? 6.2 billion cars in this crazy little box. What do we need to talk about? You got the ideas? Atoms are small, the nucleus is smaller, mostly empty space, and the nucleus is crazy dense. You good on those ideas? You okay? All right. So guys, we are now going to talk, and you need to, this is where you're going to start really writing stuff down. Guys, we've got one more thing to talk about. We've now talked about where do atoms come from? How big are they? Well, guys, what we need to do now is we need to talk about what they're made of. And that then brings us to this table, which you can thank me later for printing for you, so you don't have to write it down. Josue, join us, buddy. Here we go. He's ready. All right, so guys, you already know this to be true. Protons, neutrons, and electrons are the things that make up atoms. And guys, I also believe that you know this. Protons and neutrons are in the middle. You'll notice that this flew in. These are what we call nucleons. They are the things that make up the nucleus. So guys, there are some ways that you need to be able to think about protons, neutrons, and electrons, and we're going to put these things in this table. So we're going to work left to right, and then we're going to move to our periodic tables, gather a little bit more information, and then we're going to wrap up the day. So it goes like this. Guys, moving from left to right, first of all, let's talk abbreviations. When we abbreviate proton, write it just like this. Capital P and then a plus sign. Guys, what does the plus sign tell us? It's charged. That's why it's a proton. But then, guys, the capital letter. The capital letter tells us that it's massive. Capital letters are big letters. It means massive. So, guys, how massive is a proton? There's the answer. 1.67 times 10 to the negative 24th grams. Well, it's actually hugely small. Guys, that's a negative exponent. It's 1.67 times 10 to the negative 24th. Don't write this down, but it actually looks like this when you write it out. Guys, that's the mass of a gram, or a mass of a proton in grams. But guys, understand, that's a stinking dump truck when you're as small as a proton inside the nucleus. That's the marble inside the blueberry. But guys, here's the deal. This number is so ridiculously small that we use another set of units. They are called atomic mass units. If you can't remember that, you may want to write it above the line. Guys, AMU is atomic mass unit. And this is beautiful. The mass of a proton in atomic mass units is 1. That makes our life a lot easier. And then, guys, you already know this. The charge of protons is +1, and we're good there. So, if this made sense, you can now figure out pretty much the whole rest of the table. So, guys, neutrons also have mass. Actually, they're exactly the same mass as a proton. So, guys, what is the abbreviation for neutron going to be? Big or little? Big N, capital N, and then what's the thing up above? 0, because neutrons have no charge. Then, guys, the mass of a neutron is actually the same as a proton to 3 significant digits. Out to like 7 significant digits, it does vary a little bit, but it's really close. So if that's the case, what's the mass of a neutron in AMUs? 1. And then what's the charge? 0. You're getting it. All right, so now, guys, electrons. I don't know if you caught this with the creepy guy in the jumpsuit, but he mentioned that most of the mass of an atom is in the nucleus. Electrons do have mass, but it's very small. So, guys, if the mass of an electron is small, how are we going to abbreviate it? Which E? Lowercase e, and then the charge, which you already, do you know the charge of an electron? It's -1. We just put a little negative sign. But you're going to find out in a second that it's not just negative, it's actually -1, and that'll be important in a minute. So guys, this is a number also you don't need to know, but if you're curious, that's the mass of an electron. 9.11 times 10 to the negative 28th. Guys, that's actually 2,000 times lighter than a proton. It takes 2,000 electrons to weigh the same as a proton. And so guys, what we do is we just say the mass of an electron is functionally 0. It does actually have a little bit of mass, but it's so small that we just don't worry about it. There we go. And then guys, finally, what about the charge of an electron? Not just negative, it's -1. So guys, do this with me then. There's an amazing order to all of this. So we've got 3 particles. Guys, which of those 3 particles has mass? Which 2? Protons and neutrons. We call those the mass carriers. Now guys, which ones have charge? Protons and electrons. Those are your charge carriers. One of these particles has both. One of them only has mass. One of them only has charge. It's almost poetic if you think about it. But guys, the next thing that you need to know is this. And it's in your notes. But guys, all atoms have no charge. Atoms are not charged. So now you're going, wait a minute. Atoms contain protons and electrons, and those have a charge. So how can atoms not have a charge? Say it again. I love the way you said that. Say it louder so folks can hear. Nulls it out. I love that you use the word null. Yeah, so if you don't understand what the word null means, it means like 0, to cancel. And guys, that's actually what happens is the positive protons and the negative electrons cancel each other out. So what this means is protons always equals electrons. Well, for today, protons will always equal electrons. Yeah. What do you mean by overpower? It's actually not. It's the same number. So like, for example, take a simple one like hydrogen. Hydrogen has 1 proton. It also has 1 electron, and they cancel each other out, so the charge is 0. Now, if you take oxygen, element number 8, oxygen has 8 protons, but also 8 electrons, and again, they cancel each other out. Yes, so understand that there's a lot of interesting physics. But when we think about these relationships, we're talking about charge and not mass. Mass leads to gravity. But we don't think of gravity as being important at the scale of something as small as atoms. So if there were gravity inside of atoms, it would be a huge issue. But we don't talk about it that way. What we think about is electrical attractions, positives to negatives, and that's where the canceling happens. If it were a gravity issue, then mass would be an issue, and it would be a whole nother deal. Great point. So guys, this then becomes how we move forward. This is our goal for the rest of the day. In every one of the elements on the periodic table, you've got to be able to identify, this is part of your homework today, how many protons, neutrons, and electrons are in each one of these atoms. So guys, here's how you do it. What does your notes look like here? Beautiful. Okay, so we've got some things to fill in. So guys, in order to do this, what we need to know is we need to know some information off the periodic table about what these things are made of. So the first thing we need is the atomic number, which is abbreviated Z. Guys, looking at your periodic table, what color is Z? Look down at the key in the bottom left-hand corner. What color is Z? Big and blue. Is it purple on yours? They may have run out of ink. Yeah, purplish blue. So guys, atomic number Z is the big blue purple number, and that is the number of protons in the nucleus. Then guys, the next number that we need to know is A, the atomic mass. On your periodic table, it calls it atomic weight. But guys, if you look down at the key in the lower left-hand corner, what color is the atomic mass? Red. So the red number tells us the number of protons and neutrons in the nucleus. And by the way, guys, the units are AMUs. All of the masses on the periodic table are given in the units AMUs. Guys, this then can be represented one of 2 ways. So one of the ways that we can represent this, and you're going to see this throughout the year, is this. For example, let's use carbon as our representation. The top number is the atomic mass, 12. The bottom number is the atomic number 6. So guys, this is one of the ways we represent atomic mass and atomic number. The other way that we do it is this. We don't need the 6, because if it's carbon, it's element number 6. So what then is the 12? Well, that's the atomic mass, and we don't include the atomic number. All right, so guys, we got one more thing to do, and then we're going to start chipping away at your homework, and you're going to get your homework done today. So it goes like this. We now have all the bits and pieces that we need in order to figure out how many protons, neutrons, and electrons are in atoms. So guys, allow your eye to scan across this one more time. Z is protons, A is protons and neutrons, and now let's talk. So guys, how many protons are in atoms? How do we know? How many protons are in an atom? Atomic number is Z. Now guys, what about this? How many electrons are in an atom? Also Z, because protons and electrons cancel each other out. Then guys, and this is tricky, how could we figure out how many neutrons are in an atom? Go ahead. Yeah, good. Sorry, say it.
Could you subtract the atomic number of the atomic?
Exactly. And Gracie, you got that too, didn't you? You guys are brilliant. Guys, did that make sense? Watch my hands. This is like mass by difference. Protons and neutrons is A, protons is Z. Subtract them, you're left with A. That's neat, you guys got that. So guys, it's A minus Z. All right. So guys, here's what we're going to do. I'm going to show you one example of what your homework's going to look like, and then you're going to have the rest of the day to get it done. So guys, join me on this page, and let's talk. How much do you have here? Perfect. So guys, we're going to make this into a potassium atom. Now guys, join me and let's be sure you're clear on what you're looking at. Guys, if this is an atom, what's the circle in the middle? The nucleus. What's the circle on the outside? The electrons. Question for you. Is this drawn to scale? No, because if the middle circle was the size of a marble, how big would the big circle be? The football stadium. You starting to get it? But guys, we're going to draw it like this so it fits on our paper. So here we go. So if this is a potassium atom, guys, find potassium on your periodic table. Question 1. Do you see potassium is abbreviated K? It's over on the left, like 4 down. 4 down. Guys, looking at potassium, how many protons are in a potassium nucleus? 19, because that's the atomic number. Write it down. Right here. So potassium, Rebecca, is right there. You got it? And the big number... Oh, I just did this. Yeah. So now, guys, this. If there's 19 protons, how many electrons? Also 19. That balances charge. So now, guys, we got to do the tricky one, which is neutrons. And if you look at the mass of potassium, you'll notice that it's 39.0983. Do you have a problem with that? Because you should. Let's talk about that. Guys, why should this not be a decimal? You're a genius. Guys, you can't have a part of a proton or a neutron. Guys, what's the mass of a proton? 1. What's the mass of a neutron? 1. Electrons are 0. Protons are 1. Neutrons are 1. When you add up a bunch of ones, what kind of numbers do you get? Whole numbers. But these are decimals. Why are they decimals? Guys, this is going to be actually a question I will give you extra credit for answering, but we're going to talk about it on Tuesday. So guys, in this class, sometimes we offer you extra credit. You are going to have the opportunity to do an extra credit project either by yourself. Actually, it'll be by yourself. This one's on your own. Because you'll have the chance to do an extra credit project to not figure out why they're decimals. We're going to talk next time. But what we are going to let you do extra credit for is talk about the experiment that allows us to figure out these decimals. And we'll talk. Zach, go ahead. Are you sure? Okay. So, guys, let's then do this. Looking at the mass of potassium, 39 point whatever, that rounds down to 39. So guys, in order to figure out the number of neutrons, you go 39 minus 19, 20 neutrons. You done. But guys, here's the trick. You are going to do this for a couple dozen atoms. And guys, if we did it like this would fill up pages and kill trees. So what we're going to do instead is we're going to do it like this. Grab your homework. Guys, grab your homework packets. This is your homework on the board, and we're going to do the first few together. All this does is takes the big circles and makes them more efficient. So guys, look at what you've got. You got substance, symbol, Za, protons, neutrons, and electrons. So guys, for the first one, you are given a pant load of information. You're given helium, you're given the atomic mass, you're given the atomic number, you got everything you need. So guys, how many protons are in a helium atom? 2, because the atomic number is 2. Now guys, if there's 2 protons, we also know that there are 2 electrons because those always balance. Now we need to figure out the number of neutrons, and that is A minus Z. 4 minus 2 is 2. Yeah. I do. They're over here. I'm going to throw them to you. So now, guys, let's look at the next one. You'll notice that you're given a whole lot less information. Good. David, say it again. How do you know magnesium? Yeah, it gives you the atomic number 12. So guys, we come over here and we look at element number 12, and that's magnesium. Capitalization does not matter, but it goes like this. But then guys, we need to figure out the abbreviation, and here capitalization does matter. Big M, little g. Then guys, following that, we've got the atomic number. Now we need the atomic mass, and we lift that off the periodic table, and it's 24.3, and that rounds to 24. And guys, at that point, you've got all the information you need to finish this. So this would have 12 protons, because that's the atomic number. They already told us it's got 12 neutrons, but 12 plus 12 is 24, so that lines up. And then guys, how many electrons? How many electrons? Also 12, because those balance, protons and electrons. So guys, let's do this as a summary, and then I'm going to get out of your hair. You may want to write this down just so you have the thoughts. So guys, looking at everything that we have in front of us, and I'm going to switch colors. Guys, what does the atomic number always tell you? The number of protons. So these will always be equal. When we grade this on Tuesday, you're just going to look down the proton and the Z column, and they'd better be the same. Yeah. This is also the same for electrons until Tuesday. It's going to change on Tuesday. But let's talk about it. What if protons and electrons aren't the same? Then it's got a charge, and that's what they're called ions. We're going to do it on Tuesday. Then guys, what about this? How do we know how many neutrons there are? It's always A minus Z. So here's what you're going to do with the remaining holy buckets, 22 minutes. Guys, we are going to finish the front of this. The answers are on the wall. Then guys, on the back of this, you'll notice that there are opportunities for you to write your understandings of the analogies with the blueberry, with the football stadium, and with the cars in a box, explaining to yourself what those things mean. So guys, we are going to move forward doing that today. If you need help, please let me know. And that's going to finish up our day today. I told you were going to like this.